Good morning, ladies and gentlemen. My name is Human Zarinkup. I'm the product manager for wireless products here at MathWorks, including 5G LTE wireless LAN satellite communications. And I would like to welcome you to this second part of our webinar series for aerospace and defense entitled Physical Layer Modeling and Digital Baseband Design. As I mentioned, the first part was presented earlier and focused on scenario modeling and propagation models. In this section, we focus on the digital aspects of design, baseband and digital front end, and all the standards involved in wireless communication system design. The agenda is as follows. Following some introduction, I'm going to go through essentially 5 chapters: waveform generation, link level simulation, channel modeling and RF impairment, coexistence and interference modeling, and system level and AI applications. And finally, I summarize what we have learned. Let's go to deduction. The goal of wireless solutions is essentially ubiquitous connectivity. No matter where you are in the world, you want to be connected to internet, and different modalities are available for that. The recent emergence of satellite communication as a reliable mean of internet connectivity has been noted. Lots of LEO satellites are being deployed that is make the task of accessibility to internet available globally. We are all aware of the cellular connectivity. As long as you are close enough to a base station, you can get 5G, LTE, and other types of cellular signals, Wi-Fi connectivity at home and offices, and even Bluetooth connectivity at personal area networks. In terms of satellite communication and 5G, we have done a lot of new contributions that are related to the aerospace and defense area. In release 2021A of MATLAB, we introduced the satellite communication toolbox that addresses the main challenge of designing satellite communication and navigation systems. Those challenges include orbit propagation, trajectory modeling, access and link analysis to be able to see the moving satellite at any moment as it orbits around the Earth. The link budget analysis tools that lets us at any moment establish whether I have enough power and can close the link, and also waveform generation, end-to-end simulations needed to make sure the performance is as we expect. Now, the satellite communication toolbox has some differentiators and the benefits that I want to talk to you about. First of all, we make the task of being standard, providing standard-based functions and examples that makes the task of implementing standard-oriented solutions such as DVB-S2 and DVB-SX standard and the CCSDS easier for you. We have interactive link budget analysis apps that make the task of expanding your link budget analysis easier. Reference receiver designs. No standard contains receiver operations. They only specify transmitter designs. So we provide reference receiver applications to enable you to do end-to-end simulations, extensive documentation, and also everything we provide in satellite communication, other tools are full MATLAB source code, meaning that the open MATLAB code, you can edit them, you can visualize and see exactly line by line how the operation happens. Nobody gives you that much insight and access into detailed algorithm design. And also, if you have our MATLAB code and other tools, you can generate C code automatically from MATLAB code of our tools. That way, you can share the C code with colleagues who don't have MATLAB available to them or connect to C-based simulators. Another driving force and megatrend is 5G. As you can see, the 5G goes beyond the 4G in terms of not only enabling and enhancing the mobile broadband and connectivity of phones to cellular network, but it goes and provides ultra reliable and low latency solutions for Industry 4.0 or smart factory and other areas which require low latency, as well as massive machine type communication for the emergence of IoT uh, in our uh, in our applications. And it supports a broad range of applications, including even satellite communication. There's a non-terrestrial network body working on satellite communication in the 3GPP standard body, and also autonomous driving and connectivity and positioning and cellular networks. So 5G is driving a lot of applications and lots of 5G and any other military and aerospace connectivity is included in that. So we have a flagship product called 5G Toolbox that provides you with the main use cases that our customers have asked for. The waveform generation, uh, standard-based waveform specified by the standard body, as well as custom waveform. We'll talk to you about that. That makes your testing of your devices and your networks easier. End-to-end simulation, because you provide receiver operations beyond what the standard body gives, because you provide channel models and RF impairments, you can do end-to-end simulation, make sure the realistic performance can be achieved under various distortion conditions. Measurements to qualify at any given time how much distortion you can tolerate, and also hardware and radio connectivity to test your design, not just simulation, beyond simulation in the lab, and connect your waveforms to RF instruments and software-defined radios. Now, let's go over the first topic, waveform generation, and go in detail about that. So, in release 2018 B, we provided this wireless waveform generator app, and we have been updating it ever since. So, wireless waveform generator app, it's essentially a graphical user interface, a GUI that makes the task of waveform generation much easier. Interactively, you can select the waveform you want, either standard based, 5G, wireless LAN, LTE, this, that, or basic waveforms like OFDM, QAM, PSK, and all that stuff. And you just parameterize them, select the parameters we provide for you, and with click a button, you generate the waveform. And when you're happy with the selection you have done, you click another button and you generate MATLAB script for what you just did. So you can do a large scale testing. And we are one of the few people who actually provide custom waveform generation for 5G, LTE, wireless, and all this standard-based stuff, because every aspect of the composition of transmitter operation is a different MATLAB code and MATLAB functions. We allow you to combine them as you like. And that custom waveform generation could be very important for you testing your systems, networks, and so on. And that could be valuable. This is a example of running the wireless film generator app. You go to MATLAB, click on app, and you select the different standards. In this case, 5G downlink. And this is custom waveform generation. You go to different tabs, specify parameters. Frequency range in 5G is either FR1, less than 7 gigahertz, or FR2, a millimeter wave. And you choose a bandwidth depending on the frequency range, and you set your general parameters. Then you can go select the different components of a signal. SS burst for synchronization signal burst. PDSCH is physical downlink shared channel, the user data. You have user number one, you have user number two, and each user uses different bandwidth parts, PWDP, or different symbols in different allocation of OFDM symbols and the slots and so on. You can customize it to your heart. You can customize it as you like. And then you can visualize in time and frequency the symbols versus carriers. And then you can look at the generate and look at the time and frequency domain signal of interest. And then you can export it to either workspace, file, or MATLAB script. And you export to MATLAB script all those selections reflected in line by line parameterization in MATLAB. And we can write a for loop around this and do a lot of data generation based on this. So what have we done lately in the release 2021A of MATLAB? We provided those off-the-shelf waveforms, NRTM, the 5G new radio test models, and FRCs, the fixed reference channels, as well as custom downlink and uplink waveforms that are available to you, as you saw in the wireless waveform generator app. So any signal that is 5G or OFDM, and this, you have complete customization available to you in the wireless waveform generator app. When you look at the documentation of 5G, custom waveform is important because there's so many channels and so many signals, from physical downlink shared channel, which is like user data in downlink, and physical uplink channel, user data in uplink, and control channels both for downlink and uplink, and broadcast channel to connect to the network for the first time, and RACH or random access channel to communicate back and forth between UE and base station, different important information. All of those channels are available in 5G Toolbox, as well as all the signals, primary synchronization signal, secondary synchronization signal, DMRS for demodulation reference signal. Reference signals are pilots needed to send known data to make the task of tracking or demodulation and positioning and measurements easier. So all those signals are available to you in 5G Toolbox. As I told you, standard body 3GPP in documents 38.104 or 101 provides test models and FRCs, and we have them in the toolbox in the app as one click away for you to generate the tests that the government, the standard body expects you to pass in order to qualify your 5G signals. So the task of testing becomes much easier with 5G Toolbox and our wireless waveform generator app. Not only, as I told you, we allow you to generate waveform easily using our app, but also if you go from generate tab to transmitter tab, we can take the waveform we just created and continuously transmit it over the air using RF instruments. So essentially, as long as the computer that MATLAB is installed on is connected to a network which connects to a RF instrument, using instrument control toolbox, we just discover available instruments connected to that computer. We get the IP address, we make all the connections possible, and then, as you say, transmit in this app, we frame by frame send the stuff over that connection and transmit over the air in your lab. So you can see how easily you can generate the waveform of interest for testing, and how easily you can test it by transmitting it and then receiving it and qualifying it. Let's look at the another application, link level simulation. Yeah, when it comes to end-to-end link level simulation, you are looking at a communication link with transmitter operations, usually standardized and described in standard document. In this case, we're looking at 5G new radio. We have channel coding, DLSCH, PDSCH, modulation mappers, and other pre-coding, and finally OFDM. And then you have other areas to look at. The channel modeling for 5G, we have CDL or cluster delay line, or TDL, traditional channel models, and also receiver operations to start with synchronization using primary synchronization signal, secondary synchronization signal, and all the other building blocks to go all the way to best recover bits. And when you do this kind of end-to-end link level simulations with all the functionality provided in MATLAB, you can easily get this kind of a performance metrics, throughput, as well as bit error rate, block error rate, packet error rate, and so on. Now we have done that end-to-end link level simulations for a variety of standards, including for satellite communication, DVB-S2, for example, or DVB-S2X. These are high throughput standards used in satellite communication. We have done it for 5G NR, as you can see, physical downlink shared channel or user data throughput analysis, as well as for Wi-Fi, the latest 802.11ax standard. So, and when you're looking at end-to-end simulation, not only you're looking at downlink from base station to user equipment, but uplink from user equipment to the network or from ground station to the satellite. And for that, you see that similar operations are specified, all transmitter operations specified by standard, channel modeling also specified by standard, but the receiver operations by you. And you can see that, for example, channel estimation, equalization, these are open MATLAB code. You can take a look at them. You can modify them if you like. You can edit them and provide different profiles of performance depending on the kind of receiver you design. Again, same thing here for DVB-S2X bit recovery in satellite communication. The data comes in over the air from satellite. Then you have this header demodulation and header decoding and descrambling and all the receiver change. Each of these building blocks are MATLAB functions, and all together they take the signal, which is distorted by channel by RF impairments as this, and it ends up just before demodulation as this signal APSK, which is subject to successful decoding. And also the RF front end and synchronization is important. Again, nobody provides you in the standard body with the way to synchronize or the way to compensate for the effect of RF impairments, like compensate for Doppler shift, compensate for phase error or carrier noise. And these are the functionality provided in the toolboxes to just let you model properly the RF front end, which is important for end-to-end link level simulation. Not only we provide you with all kinds of operations, but also every single part of the DBS2 and DBS2X in satellite communication, all the modulation and coding modes are included, and single and multi input streams, and we have constant and variable rate coding and modulation. So all those techniques that make you optimize your DBS2X and other things are included with the toolbox. Let's take a look at the channel model and RF impairments section. Now, channel modeling is an important area, and MATLAB has a lot of channel models in various products. Look at the profile here, Doppler shifts as a result of movement, and as you move, the way you rotate your constellation is reflected here. And you have propagation losses, free space path loss, or ITU P.618. This is the standard International Telecommunication Union ITU provides is P.618, which has been in use for many years. It provides all the profile of rain, fog, and precipitations, and that covers different portions of the Earth. So no matter where you are putting your ground station or you're putting your satellite as it moves around the Earth, you can use that and look up and use those kind of propagation losses. On the stochastic or statistical part, we have the classical Rayleigh, Raytheon, and 5G TDL, transfer delay line channel models. When it comes to MIMO and massive MIMO transmissions and the corresponding effect on the channel modeling, we have the 5G and our cluster delay line. If you're using multiple antennas in transmitter and receiver, the effect of that is reflected in the channel modeling for spatial channel modelers, including the CDL, and also Wiener 2 channel models and all the channel models of Wi-Fi. If your transmission is best modeled by a very narrow beam width, so the beams are very narrow, you can think of those transmissions as rays. So ray tracing, which are different algorithms for that, is also included for your channel modeling purposes. Now, nothing in life is ideal. The RF circuitry adds distortions and linearities. You can see here phase noise and carrier frequency offset, IQ imbalance, and those affect the performance. So you have to model the effect of RF circuitry on your overall performance. And you have to compensate at the RF front end for those effects. Carrier synchronization loops and symbol timing synchronizers that we saw from PSS, SSS for 5G, DC blockers, and DPD for nonlinearity. Now we have an example here on the receiver side. It is for satellite communication as well as communication toolbox that you specify the system parameters. How far are you from the ground station? What frequency band using? KU band, C band, whatever. Atmospheric conditions. What kind of a essentially propagation loss you are modeling, and all kinds of information about the RX and TX antennas. And then you tell us your estimate, parameterized estimate of your RF impairments. How about your noise temperature, your power amplifier back off, your Doppler shift, amplitude imbalance, phase imbalance, DC offset, and you ask whether you want to correct for those Doppler or mobility shifts or amplitude and phase and DC offsets, and you can simulate and look at the results with and without those compensations. Now, about coexistence and interference, that's another topic of importance for wireless for aerospace and defense. Now, as you can imagine, at different frequencies, either we have adjacent channel interference or interference in the same band. Now, for 2.4 gigahertz, Bluetooth, Zigbee, Wi-Fi, even your microwaves operate at the same frequency, provide interference in the same vicinity. For 5 and 6 gigahertz, Wi-Fi, LTE, and 5G have common frequencies of interference. And even for 60 gigahertz millimeter waves, Wi-Fi, 5G, and drones have interference. Here we have an example where we use the 5G as the interference for the Wi-Fi. And we look at the transmission rate form at 5.95 megahertz, and interferer is the 5G at 5.980. And we look at the EVM per subcarrier as metric, channel power, EVM per OFDM symbol, and with and without interference. And we show you how you can quantify and then compensate for the effect of interference. Finally, we'll look at the system level aspect of your simulation as well as application of AI or artificial intelligence techniques in wireless communication. For example, every time you have to share resources, frequency resources, data in time, frequency, even transmissions over multiple antennas to different users, you have to essentially devise schedulers. Now, schedulers are the rule-based, so you have some rules. In this case, round robin, meaning allocate in a very temporally sequential way, or proportionally fair, or best CQI. CQI stands for channel quality indicator. So you look at the channel, and based on that, you schedule. But different schedulers are important elements to allocate different resources, even the modulation and coding scheme, depending on channel conditions. And we have in the 5G toolbox the beginning of system level simulation with very simple schedulers as well as the techniques to allow you to make it as complicated as you like. Now, not only for scheduling, but also for a lot of applications, the AI or artificial intelligence, machine learning, deep learning, reinforcement learning, are finding its way as important elements in wireless communication. And all of them have this sequence or this workflow in common. First, you have to prepare your data. Deep learning, machine learning, reinforcement learning, all of these techniques require lots of either data or lots of simulation time. So you have to do pre-processing, clean your data, prepare your data, label in supervised learning, meaning that if you know the nature of some data, you can use them to label them so it can be used for the subsequent AI modeling, and generate lots of synthetic data. You have to augment your existing data so you can go through all kinds of possible data and simulation to make your AI modeling representative. After data generation and preparation and cleaning up and so on, comes the stage of AI modeling. In AI modeling, you have to have either from scratch develop AI model, this deep machine learning or deep learning networks composed of multiple layers, and each layer corresponds to uh, a bunch of processing, or you have to exploit existing AI trained networks. For example, AlexNet, GoogleNet, ResNet, all these things, which are essentially designed for images. But using transfer learning, you can transfer data from audio or speech or wireless communication, IQ samples, map them to a kind of an image-like signal, and then use the ResNet, AlexNet, those pre-trained data, and then transform them back all the classifiers and so on to the original domain. So that's what AI modeling means, and you have to also try to run as fast as possible with as much as data as possible. And then after you train your network, your AI network, and you're ready, you have to put that trained network into your system, integrate with your system, and do the testing to see if that trained data actually reflects the reality with the either over the air captured IQ samples or other synthetic data, and we can verify whether the process has been done properly. After everything is done in simulation and testing, you have to deploy it on embedded devices, enterprise systems, cloud, edge, and desktop, and so on. This is an example of how we are creating pre-labeled synthesized data. It could be electrocardiogram data, it could be speech, audio. In this case, it's IQ samples from wireless communication. We transform them either directly to a time frequency representation like spectrogram or resource grid and so on, and you train the network. Or if you're willing to uh, describe your network in MATLAB from scratch, you don't even have to transform. You can just directly take the IQ samples and train your network. And then now you have that deep network model trained. In the testing stage, you get a new signal, an over-the-air signal or so on, and do the same transformation or without the transformation. Apply the pre-trained network and do the classification regression, all the stuff you do with AI. Now we have chosen an application, cognitive radio spectrum sensing. We are looking at a large swath of frequency from minus 30 to 30, 60 megahertz of frequency constantly. And in that swath of frequency, we expect to find either 5G, LTE, or noise. And we monitor that and label 5G LTE in our training process, and then use it in the testing process to distinguish between 5G and LTE signals. What's the workflow? The workflow is generate 5G and LTE signals using that wireless waveform generator app I told you about. That app enables you to generate a vast amount of data because every parameter can be modified. Those modified parameters can be put into a script. You can write for loops to go through all possible combinations and generate a lot of 5G and LTE class of data. Following that step, you can actually take that signal, time domain signal, and calculate spectrogram, which is a time frequency representation. And essentially, because spectrogram is an image, and you label them either using our computer vision toolbox as well as other tools, you can label those pixels on the image, which is a spectrogram image, as 5G, LTE, and noise. Now that we have labeled them, use our deep learning toolbox, and you import that DeepLab V3 Plus ResNet 50 as a pre-trained network that has been done for us, and we connect to it. And now we're doing transfer learning. So essentially, the last layer, we apply a transformation to go to images and back. Now that we have that, we are using a transfer learning, using pre-trained data on these spectrogram images, now we have to go through all kinds of iterations. We optimize what they call hyperparameter. In Deep Learning Toolbox, there is an experiment manager, allows you to go through all parameters, when to stop updating, how many iterations, what parameters are subject to modification, and so on. Now that you have done that, you test with static signals. So you compute these normalized confusion matrices. For 5G, we get 97% correctly done. For noise, 97%. But for LTE, it seems to be 87%. So now you go and test with captured over-the-air signals with SDR connectivity communication toolbox and see where is it that it's failing. And you realize that we haven't done enough 10 megahertz LTE signals. We have done too much 5 or even lower. So you augment your training with 10 megahertz. You do it again, enhanced training, and you do that for a large swath of data. Finally, after all that classification and stuff is done using these tools, you have to deploy it to processors with best-in-class performance. If you're going toward embedded devices like CPUs and GPUs and FPGA, we have products for that. We have a deep learning HDL toolbox for FPGA. We have GPU coder for GPU. We have MATLAB coder, Simulink coder that generates C code for you on the CPU. And if you're going toward desktop and enterprise applications, .NET, and so on and so forth, you can use MATLAB compiler, and using that, you can deploy it for large-scale deployment onto enterprise systems and desktop. As I mentioned, Deep Learning Toolbox is a very convenient way. In 5 lines of code, you can actually take your network and deploy it onto FPGA and then see how much faster it will run. So to learn more about all the stuff that I told you about on physical layer, please look at the wireless communication product pages. Most of them written very nicely about different features of different 5G standards. And look at our wireless communication solution page. To summarize, in MathWorks and MATLAB, we provide new capabilities for efficient design of physical layer of wireless communication system that enables not only end-to-end simulation, but also, waveform generation for testing, channel modeling, RF impairment modeling, coexistence modeling, and performance in presence of interference signal, system-level simulation, and application of AI, deep learning, and machine learning for wireless classification, regression, and other AI problems. Thank you very much. I hope this was useful for you. Thank you.